Hello, everyone. Welcome to the session. Thank you for staying at the session, and thanks to our panelists. I guess we can start now. Could you please like spend some time talking about yourself, your projects, your companies, and how you came to work on GKP and scalability? So please.
Okay, so I'm Chiro from the founder of Origin Networks. So we a project that we try to improve the scalability of the computation. And right now we do apply the zero knowledge proof to our product to build up the ZK WASM. And also we focus on how we could improve the data correctness, data availability, and to build the first verifiable data pipeline. And then just like when we do research about verifiable computation, so every road will bring us focus to the GK proof. That's why we are here today. Yeah.
Yeah, Xinjiao, everyone. My name is Sibuk Chen. I'm from Stackware. I'm the developer advocate. So obviously Stackware is an $8 billion company. We are really focused on scaling Ethereum. We're doing layer 2 with a bunch of inventions, including stacks, including Fry, including layer 3, other stuff. So yeah, if you want to know more about Stackware, definitely reach me out. We have a booth over there.
Hello. Hi. So I'm Nam from Kyber Network. We are a DeFi company that have solutions both for liquidity provider and also for taker because we have an aggregator. And recently we are also launching a new feature called training soon. So it helps you to trade smarter. So if you would like to learn more about product, we also having a booth out there. You can check it out. I'm the applied cryptography research lead at Kyber Network, and I'm in charge of conducting research on scalability and also privacy, so that we can enable mass scalability and privacy for our products, the DeFi products at Kyber. And I only recently came back from Europe, so I did my PhD there, also in cryptography, especially in privacy. So that is also how I got into doing this ZKP research. Thanks.
Hello everyone, I'm Janmajay. I work at PSC, which is Persian Scaling Exploration Group at Ethereum Foundation. And I mostly work on ZKP stuff, developing tools for ignition circuit and other developer stuff.
For the next question is just like a brief, probably educational question to the audience for people who might not know. Would you please describe briefly what GKP is and how it can be used to solve some of the practical problems?
I can take on that. So ZKP in layman's term is obviously the full is a zero knowledge proof. So in layman's term is you're doing something without somebody's monitoring and to make sure it's correct, right? So basically what happened is there's a proof, there's a prover and there's a verifier. The prover can prove something without you don't need to know any knowledge about it. And we send the proof to the verifier and the verifier can verify whether it's correct or not. So it's all backed by the math and the cryptography. Yeah, please add on to that.
So just to sort of explain in very simple terms, let's say that I want to prove to you something, right? So I want to prove XYZ to you something. And I can do that in many ways. But what if, let's say that I have a big computation and I want to give you a small proof for that, which you can verify in like within seconds. That is succinctness, and which is one of the properties of zero knowledge proofs. Now, let's say that I want to prove to you something without letting you know what the inputs are. And that's where the zero knowledge comes in. And that's the zero knowledge part of zero knowledge proofs.
think I have like a little more dummy approach. Like just like zero knowledge proof is you telling someone that you love them without telling someone that you how you love them, and actually it is zero knowledge proof working how it's working.
It's actually a very good analogy. Like somebody showed me, I just tell you quickly. Let's say I have moderator's number, right? So I don't have to prove you guys how I got them. I just have to pick up my phone and call him. Right? If his phone rings, which means I've got his phone number. That's kind of like zero knowledge proof. Right?
Thanks. So, so zero-knowledge proof is a cryptographic technique that it allows the prover to convince the verifier that something is true without revealing anything new to the verifier. So, this anything new because the verifier could know something beforehand. So you couldn't revert that knowledge of the verifier. And, two major use cases of a zero-knowledge proof. First of all, we have seen it, right? Which is the scalability, the application of ZK rollup. So it is, the use cases of verifiable computation too. So you perform a very heavy computation. So you are very, very powerful server, but then you are able to give a result to a weak client, which is the verifier. That is, could be a mobile phone or it's just a web browser. And you can convince the weak client that you have performed the heavy computation correctly. So that is the first use case. And of course, the second use case of zero knowledge proof comes from the term zero knowledge, is privacy. So, you can perform some computation, you can tell somebody that you have performed a computation without even giving the result. And you still be able to convince the verifier that you have done the computation correctly. So I think that is the general summary of the ZKP and the two major use cases of the ZKP. Thanks.
Cool. Yeah, so ZKP has recently been mentioned in like some of the hot hot ZK scheme, like Stark, Snark, Plunk, and that's used in ZK EVM. So you could like explain to the audience what are them, what are they? So maybe start with you. Could you talk about Stark?
Obviously, I'm from Stackware, so we invented the stacks. So what stacks? Stacks there are some unique properties of stacks. First is trustless setup. Right? Everyone can run stacks. If you snack, they require a bunch of guys who trust each other to serve first. So that's the first major difference. The second, actually, the prover time is logarithm n, the complexity. But the verifier is only logarithm n. It's much faster. So for the prover, we have to have some special machine to prove this. But as the verifier actually lives on the Ethereum layer 1, it can like verify in a very efficient way. So that's why how we scale the Ethereum.
You want to talk about Snark? That's what you are using, right? Yeah.
Actually, right now my team is doing research about Plum, but and yes, we do research in Snack, but we not use GK in our product. We just use Snack, and to prove the honest of the statement. And actually, when I try to use like discover many kind of zero knowledge proof and choose to use Snark because the proof size is small, and because right now the infrastructure and also the blockchain and the storage enough have the capacity to store the big proof. That's why we choose the Snack over Stock. And I think it's maybe in the future there are a lot more space for people to improve the, the, um, the proof size and also in the proving time.
Well, sure. So, Plong is the name of a ZK snack. But I think that to be more precise, it's the name of the amortization scheme, which is expressive and intuitive enough. Uh, it is even more intuitive and expressive than the previous amortization scheme that we used before, which is R1CS. So it is currently adopted by a lot of team. I believe also the PSE team is adopting Halo 2, which is Plonki's aromatization combining with sorry with KCG. So yeah, and yeah, so Plonk is popular. I think that tomorrow we'll have a tutorial on Plonk, and then you will learn more about it.
So I'll take ZKVMs.
Yeah.
But before that, I'll just add to what he said about Plonk. Basically, Plonk enable you to have universal setup. That means that rather than running setup ceremony for each and every circuit, you need to just run it one and you just need to, I mean, all these circuits can use a common one up to a certain number of constraints, which actually sort of benefits in a case that you don't have to. So this reduces the possibility of someone cheating in cluster setups. Another thing that Plonk did was that Plonk reduced the overhead cost for the prover drastically compared to the previous constructions of universal stars. Now, what is ZK EVM? ZK EVM is sort of so a true ZK EVM. It's a it's a effort towards building. Sorry, it's an effort towards writing circuits so that we can prove EVM computation, and that's it.
Yeah.
Excuse me. So before the next question, I would like to add a little bit on the comparison between SNARK and STARK. So oftenly we try to compare them, right? So SNARK has short proof size and also low verification cost, and STARK is on the other hand have low proof cost, but then have large proof size and relatively large proof cost. Sorry, verifier cost, but it doesn't have to. So like a system of ZKP doesn't have to be exclusive of Stack and Snack. You can actually combine them. So you can have the client that runs Stack. So you reduce the effort of the client, and then you can use Snack to aggregate the Stack proof recursively. So you have low verification cost and also short proof size on the Ethereum layer one, which is I think that it achieves the best of both worlds effect.
How about in terms of like post-quantum computing? Do you have any comparison between Stark and Snark?
Stack out of the box is quantum resistant. So it's not even the quantum computer out cannot hack the Stack protocol, basically.
And Nam, you mentioned recursive proof. Could you please like explain it a little bit and how it can be used to improve Stark and Snark and Plonk?
So I wouldn't call it improving, but it is a way that you can actually bundle more transactions into one proof. So like when we're using a ZK Snark or even a ZK Stack, we will hit the limit of the number of transactions that we can bundle into one proof. So that is what we often call the size of the circuit. But then what if we use the circuit to verify other proof? So then you can bundle more proofs into the circuit, and then you can do that recursively, as many layers as you want. And furthermore, you can actually generate proof in parallel and then aggregate them. I think that at Starkware, you have like 128 provers at the first layer, and then you reduce it by two until the very first layer. Then you have one single proof of the of the stack. So you can bundle even more layers.
So actually, I'm not too sure. I think Stockware invented this new concept called layer. We ultimately is doing scaling of Ethereum, right? We are a layer 2 solution. But like we introduced the recursive kind of snack technology, which can be enabled to the layer 3, right? Layer 3 is more like an app chain. So any very heavy user interactive kind of applications can be resides on the layer 3. We're using recursive kind of proof to do this.
And also like Plunk is kind of like a general paradigm. So like, could you talk about like that generality of Plunk in terms of like building a flexible snack scheme?
I think the point is like Planck opened a new ability for people to replace one component of this by a different methods. Like you can turn a plank into stock by replace the fries in, into it. And it's the open something new, like you mentioned about the quantum computer and quantum security, post-quantum security. Like right now, we can use NOC, and later on we can switch to dark or stock to be safe with the when some people have the quantum supremacy. Yeah.
Just to sort of add on that, basically, the way a proof works is that you've got an arithmetization scheme, and then you've got a commitment scheme, right? So Plonk arithmetization is very expressive, and you can express a lot of competitively, like you can express a lot of computation in lesser constraints. And as long as you're able to do that, the proof of cost reduces. And then you can sort of use any commitment scheme at the base layer. So these commitment scheme could be KGZ or Fry. And which is why you sort of see that, for example, in Plonky 2, you've got Fry. In Halo 2, you've got KGZ. Yeah. No, I'm sorry. In Halo 2, you've got yeah, yeah, IPA. And in Halo 2 PSC, you've got KGC.
Yeah, so the session is called Ultimate Scalability with ZKP. So like, could you explain why scalability with ZKP is ultimate?
I think that's the roadmap of Ethereum, right? That's set by Vitalik and Ethereum Foundation. So basically, we know Ethereum currently is maybe 15 transactions per second. It hits the limit. During the last bull run, like Ethereum cannot scale, right? You mean the NFT costs you maybe like $1,000, and extremely slow during the like NFT mint, the other side kind of metaverse, the Bored Ape kind of land. So there are lots of our team working on the layer 2 solutions. Right, there are two kind of major methodology. One's using optimistic rollup. Obviously, the team is Optimism and Arbitrum. They are doing a fantastic job, but they're using optimistic rollup, which is assume all the transactions are valid, and they have a window of 7 days. Somebody can challenge. Right, this will introduce some problems, right? But on the another realm, there's a ZK kind of rollup. We're using ZKP knowledge, zero knowledge, ZKP to do all the validation. So basically, we have a proof, right? Generate a proof, bundle all the transactions. We generate proof and send to the layer 1, and the layer 1 as a verifier to see use math and the cryptography to check whether there's any wrong data or the fake kind of transactions, right? That's kind of make sure everything is working intact. So that's why I think Vitalik and the Ethereum Foundation or Ethereum community think that's a better tech, right? The ZK technology is better, and it probably is the end game for the layer 2. That's the ultimate solutions. But ZK is quite difficult, right? So that's why there are so many teams working on this field. Yeah, we feel tremendous honored to be part of the game.
So, in sort of very, very simple terms, uh, there are certain constraints for a blockchain, right? Because it is decentralized. What you want is less amount of computation on the blockchain and less amount of data. And turns out there are two schemes that can support this. One is optimistic, and the second is using zero knowledge. Uh, and now Ethereum is sort of exploring both of these options. And I think that as as the as you can sort of see that the as we are sort of like progressing towards scaling Ethereum, we are seeing that a lot of new schemes are coming in zero knowledge where the proof of cost is really less. So initially we thought that building a ZKVM, not ZKEVM, but ZKVM would be really hard. Now turns out like that problem is more of a solved. Now the problem is that how do you build a completely compatible ZKVM? So yeah, I think both options are being explored, and let's see what turns out the better one.
I think I will mention a little bit about the role of ZKP in the consensus. Right now, for Ethereum blockchain and for several blockchain, people need to repeat the computation every node on the network to verify the result. That is not the efficient way to how we should improve it. So right now, like PSE built the ZK EVM Taiwan, and actually it can help another node can verify the block without repeat the computation. And I think it is a new ways to help scale the blockchain and also uh, s- like secure the consensus, and even it's open a new ability to integrate the general knowledge proof into the consensus.
Nam.
Yeah, so I mean, we are looking at two scaling solutions right now, right? So optimistic rollup versus ZK rollups, but they are not the first attempts of scaling blockchain in Ethereum. So we have seen in the past remote attestation, like using trusted hardware like Intel SGX, or you can also see sidechain using multi-signature or threshold signature, and also state channel plasma. But even together with optimistic rollup, they have the problem of there is always a trust assumption, which is removed by the ZK rollup. So I'm also a ZKB believer. So it can be a little bit biased, but also from the point of view of the cryptographer, ZKB is like a field that has been explored like rigorously for the last 20, 30 years. And I don't think in the near future we will have something that is better than ZKP in verifiable computation. And also, if we want to support privacy, then ZKP is exactly the right tool. So when we are exploring ZK rollup, it is from my point of view the finally moment. People, congratulations, you have found the right tool. So like ZKP may not be the to be precise, it is not the ultimate scalability, but it is going to be part of the ultimate scalability. And also it will be at the core of the ultimate scalability of Ethereum and other blockchain.
Yeah, so cool. Yeah, so ZKP has been trending, has been very hot with like several new developments. So yeah, so could you please talk about some of the recent ZKP developments, like both in terms of technical and also in application?
The fun fact is the ZKP technology won't be possible until recently. Probably just 4 or 5 years ago, there are breakthrough in the math and the cryptography to make this all happen, like Fry, like this KCG, all the stuff, if I'm not mistaken. So this space is evolving extremely fast. Just to Maybe 5 years ago, the machine is not fast enough to generate proof, but now it's getting better and better. But bear in mind, generate proof is not a trivial job. It's intense. It requires a specific machine to generate proof efficiently, basically.
One of the things that one of the recent things that I find really interesting is having lookup arguments. So basically, when you write a circuit, you've got constraints. You have to define certain relations between input and output. You do that using polynomial. But thinking about such stuff in terms of polynomial is pretty hard. And with lookup arguments, you can sort of simply say that, okay, fine, there's a lookup table. The value belongs to this lookup table. You can simply look up the table, right? So, and that makes it really easy for writing circuits. Now, it turns out that having more lookups is very expensive in terms of proof of cost. So what happens? So it's very expensive, which is why we do not have that many which is why we cannot fit in a lot of lookup arguments within a circuit. But with new recent schemes like Coq and Belu, if I am sort of if I'm calling it correctly, uh, you can have sort of a lot of lookup arguments. So I think that as we move forward, we would see a lot of interesting developments with writing circuits, basically using lookup arguments rather than having to define them with polynomials. And if someone is interested, you can actually go and read about this on ZK Research. It's a post that Barry White had, and the title is Lookup Singularity. So it sort of goes about like how we can sort of reduce the complexity with circuits, like reduce the complexity of writing circuits with lookup arguments.
Yeah, so just to add to what Jay has said, I think that there are like two things that are interesting going on recently in the ZKP field. First of all, the reduction of the approval cost using improvements in lookup arguments, and also the new hyperplot, which which replace the heavy computation with the lighter one. Another thing that I would like to mention is like the building of high-level languages that are used to express the circuit. So you see, like Polygon has the polynomial identity language, which allows us to describe the circuit in a more intuitive way. So it reduces the error when you are building the circuit. In the past, we also have Circle. And also Aztec recently have this NOAA language, which allow us to also describe privacy-enabled circuits. So we can have additionally privacy in the application. So thanks.
So the thing is, zero knowledge proof is not just you only use zero knowledge proof without blockchain technology. Actually, it have many applications, even in the improve the security for IoT device, and also do the verifiable audits, or even in finance reports. That is something that make like ZKP actually make everything to be possible. Yeah.
So what's the current challenge to ZKP and scalability, and what are the possible solutions for them?
I think the challenge is, I mean, you need more developers writing circuits, and for that to happen, we need to make it really easy to write circuits. And as I said before, lookup arguments sort of help you reason about computation much more easily than polynomial constraints. So if we move toward that direction, then you would have a lot of people writing circuits, thus a lot of applications using circuits, because zero knowledge proofs are really useful.
Yeah, so just to add to what Jay has said, yeah, so I agree with you, right? So first of all, we need to learn how to write circuit. And second, after you have written the circuit, you have to assure that the circuit you have written is correct. So I think that the development of high-level language and also the formal verification of circuit are two main challenges that we should try to tackle right now. Because, yeah. No, I'm finished.
Just one major point that I think is really important is that most of the documentation for zero knowledge circuits or writing circuits is in English, and a lot of people, especially from Asia, are not that familiar with English. So it takes the added effort to actually get like just to write circuits, right? So we need more people, whether technical or not, sort of translating English documentation into native languages so that people can start writing circuits. So if someone is up for that, please do let us know.
I just want to quickly add to our ecosystem, Stackware, right? So basically, we kind of have a StackNet, which is a layer two kind of permissionless chain. So obviously, we're looking for developers. We invented a language called Cairo, so you don't have to manually write those circuits, right? Just it's a high-level language. You can just write Cairo, and it will be efficiently transfer or compile down to the circuits. So probably that's kind of an easier way to get into the ZKP world.
I think for me, the main challenge is build a bridge between like software engineer, academic, and also security. So I need three metrics to ensure that to make sure that the program is safe, the circuit is safe, and everything going to people who develop it have the insight of the what they have done.
especially security. Yeah, so we have more questions because it's a very interesting topic. But like we got to sum up. So probably with the visions, like do you have the vision for ZKP in the 5 or 10 years? How ZKP gonna be applied in practice? Not only blockchain, but could be any areas. So
Well, I just hope that we are able to reduce the prover cost a lot so that you can sort of generate zero knowledge proofs on mobile devices. And once you're able to do that, then you would have very, very interesting applications like just imagine people are able to generate proofs for something on mobile devices, right? So I'm just hoping for that.
For us, we working on general purpose runtime. So the thing I want to see in the more like in 10 year or even more is like have a huge improvement. So people actually can create like high performance runtime. So we can actually build the decentralized DApp because right now even we have a DApp, the DApp is very slow and we cannot use.
Yeah, I just want to add to that. Actually, currently everything is focused on like blockchain, scaling Ethereum, using ZKP technology. But actually, ZKP is much more, right? It can benefit the human being's life in a much broader way. So, but now ZKP is probably a perfect match to the blockchain world. But in the future, the ZKP in Mandarin, right, you don't have to provide any kind of knowledge and can prove something without people watching, right? So that's a tremendous powerful. So in the future, I think there are more and more since the technology become more and more mature, it's more accessible to the basic human beings. The ZKP technology can be used everywhere in our life.
Yeah, so just to add, like we have Ethereum smart contract in 2013, right? So, and now we are in 2022. So we can just look at that and try to project what ZKP could be in 5 or 10 years. So it's just more adoption, be more mature, more developers, and more in the ecosystem. So not just for scalability, but we have also more privacy and maybe get to onto mobile phone and get to everyday life.
All right, cool. So thank you for staying with the panel, and thank you panelists for your insights in the area. So maybe a round of applause to the our panelists. Thank you.